Looking good. Okay, great. Yeah, so as Nico mentioned, we've been doing a lot of work with our sensors here and trying to translate all those data that come in into some helpful information. So we're using AI, or let's just be honest, we're using models that we're hoping can help simplify workflows and just make some things easier. There's so much that bogs us down in a day when you have to evaluate sites and make quick, uh, critical decisions. You want to be able to do that with some confidence. So hopefully we can help with that. So some of the preamble of why we got to autonomous sensors here at EMS is that point in time estimates are great and they're the standard, and you can develop some very great data sets with them. But sometimes, for various reasons, they might not give you the best information to make the decisions that you need to. And here's just a few reasons. So, for instance, you just take a tiny sample, say when it comes to groundwater or soil, you just take a tiny sample of a few grams or a few milliliters, and you're inferring some results about a large area from just that tiny sample. The Just based off the recent end to the NHL season, I was just thinking that a good analogy is like you watch 1 minute of a hockey game, and in some cases, you see that 1 minute, you know exactly how that whole game's going to go. But other times, it might not be as indicative as you think as what the outcome's going to be. Another reason is that samples vary quite a lot day to day, and particularly seasonally. You can also have variability due to sampling technique, whether you're using low flow or Baylor approaches for groundwater. You can have a lot more recharge from rainfall that'll dramatically change your results. And then one of the more, I guess, hits home kind of reasons is that manual sampling it's expensive, and it's kind of difficult if you've got a lot of sites in your portfolio to try to triage that. So potentially some questions get left unanswered, like how do changes in water table affect plume stability? As you know, you have a rising and falling of the water table throughout the season, and that goes through your smear zone and changes the dynamics there. You know that there's some kind of natural source zone depletion going on, but unless you're measuring it in real time, you don't have a good handle on what rate that's occurring at. Or it could be that there's some kind of active remediation, whether it's an SVE, an MPE, or some biochemical biostim. You want to be able to, because some of those systems are very expensive to operate, particularly over a season. And so it's better to find out sooner rather than later, say when you're reaching that, say, diminishing return. It'd be good to be able to, if you could, say, shut off the system sooner, that could save you a bit more money that could be put towards something else. And this is a comment we got from one of the engineers on our team. She's on our technical sales and has a lot of conversations with site managers and consultants. And they said we spend a lot of time and effort to sample sites year over year up to a decade to try and move a site to closure. It's a difficult process each year to prioritize sites and budget. So we want to understand risk and get liability off the books. So there's the timeliness here. We were just at the Patel conference in Denver, and we see that a lot of sites often are on the books for decades. And if you could shave a few years off that would be really helpful. So backing up for a second, we can talk a little bit more about, I guess, EMS's story. So it started off as a bioremediation company, and it was co-founded by Dr. Steven Siciliano at the University of Saskatchewan, who's the industrial research chair, worked for a long time with Federated Co-op, and they were developing, Steve and his team were developing these biostim solutions to try and remediate mainly a lot of gas stations. And as they were doing this, this is students doing their masters and their PhDs and that sort of thing. And so they apply a treatment, and they might have to wait a few months or possibly up to a year to be able to, have somebody get a soil sample or get a water sample so you can see how that treatment is performing. So it's kind of a slow return to be able to assess those treatments. So they thought, well, is there some kind of automated ways? There's a sensor we can put in. And so they looked into it, and there was some readily available tech that hadn't been applied in this space. But I'll talk a little bit in a couple of minutes more about it. But basically, we built these sensors. Okay, now we can monitor hydrocarbons so we can get an idea quicker about how these treatments are responding. And then one of Steve's PhD students actually mentioned, you know what, this sensor is actually really could be really helpful for natural source zone depletion. And so they ended up working on a trial with FCL and got a site in back in 2021. And that site's still going, and the results are looking really interesting. But then the question came up, okay, well, the main bread and butter for data that come in is from water sampling. So can these sensors be used in the waters? Well, we'd have to make it more waterproof, but the fundamental chemistry and the sensors would be the same. So then we started putting these in groundwater. It's like, well, how can we, this is a lot of data coming in. And so what? Is more data necessarily better? And so we hired on a PhD in hydrology who came on and developed these groundwater models based off ModFlow, which is the United States Geological Survey standard for groundwater modeling, and found that these could be really useful and really insightful, particularly for scenario management, that put a bunch of data, whether it's from a phase 2 or just an annual sampling, caps and wraps. You can put those data in. You can get an idea of how is my site in terms of its plume characteristics now. And so I thought, well, we could actually tie our sensor data into this and get real-time updates. And so that's what today's talk is about. So why autonomous sensors? Well, one of the nice things that I feel is maybe at the forefront of people's brains right now is that the more time you spend on the road, the more chances there are for an accident. So you can get gains in your health and safety and environment, less site trips. And my understanding is that it's hard to find, there's not as many folks to fill these roles as are needed right now. So it kind of limits the amount of sites you can cover. So it'd be nice if, say particularly remote sites too, if those could be automated, we're reporting there, and we can have our staff go and do the manual sampling on sites that might be a little bit closer and easier so they can get a little more bang for their buck. So it can help lower costs and also triage sites. And then the sooner the data come in, the sooner you can make decisions on whether it's how effective a remediation treatment is, or you're gauging seasonal effects on the plume. And also, some of these gases are very episodic. So in particular for natural source zone depletion, you want to count for gaseous ebullition, which is, you could say that and get uninvited real fast to a lot of parties. But the reason why that's important is because, getting back to methane, there's these processes that are going on as hydrocarbons are breaking down, mainly fermentation, where it's anaerobic, and you get these periodic releases of bubbles. So you can have a lot of activity, you get a release of methane, and then it kind of stagnates for a while because there's the activity from the microbes, and there's also just the physicality of those bubbles escaping from the water to be detected by a sensor. So if you're measuring in real time, you're catching all these events, and so you can get a more accurate picture of how depletion is proceeding. And this picture here, just as an aside, is actually ChatGPT's interpretation of gaseous ebullition. So it's not actually any scientific rigor. It's just a nice representation of, okay, we got these bubbles that are making their way to the surface. And there's a lot more, maybe some aliens in there too. And the one thing that resonates with me about having autonomous sensors is that you can capture trends a little bit sooner, a little bit more robustly. So for instance, here we've got November, it's a fall sampling. Say there was 3 wells that got sampled. Okay, great. We got this distribution. Um, When you compare those to what the data are doing over time, you're really just getting a small snapshot of like, okay, this is how this site could be doing at this particular day of the year. So if you're, sorry if anybody's colorblind, but the green dot, you might have some robustness there. It's okay. This is indicative of what's happening at this location over time. But those other two might not be as robust. And so you might not paint the most accurate picture of what's going on at a site. With this next figure, this is where we've gone one step further and interpolated a plume using those sensors. And so it's plume area on the Y and it's time on the X. And then you can see the plume fluctuating through time. Now, if we do a thought exercise here, where let's say that we do two fall samplings. We get these 2 points in time. You might interpret those data as, oh, our plume is growing. This is a problem. Or a more rosy picture, you got a fall and a spring sampling. It's like, oh, it's shrinking and it's going away quickly. This is great. We can get this off our books next year. When in reality, it's a little bit more of a more nuanced picture that if you look at the overall trend, yeah, there's some seasonal variability. It goes up and down, but overall it's shrinking, but not quite as much as that latter example might suggest. So this is where autonomous sensors can come in. So this is our water sense here. This is the latest design where it hangs. It used to go down an existing well and have to be built so that it sits on the bottom. But as you know, depending on the status of the wells, it could be breaks in it. The wells might not be as deep, or they could be deeper than the last data collection suggests. So to circumvent all that, you can just hang it from the top, so it's much easier to adjust. So I've actually got one here. So right away. But here's, is it going to show up? There we go. So we got the sensor here. You can see where the input for the gas is. Maybe it's the problem with these backgrounds. But yeah, I'm just holding it here. It's not all that big. There's a spool here that all the cable is on. So that's the real deal. Go back to this mock-up. So it measures in the vapor carbon dioxide, methane, total hydrocarbons, and also temperature and pressure, which are required for the chemistry calculations. So the whole thing gets put down into the groundwater, suspended on this cable, so it's very easy to pull it up if you had to take a sample and put it back down. And how it works is that it's waterproof, and there's a membrane here that allows gases in but keeps liquids out. And then the data are measured continuously. It's usually every half hour, and they're stored in the cloud. So there's no having to go to site to actually download these. It actually goes through a gateway, through your cell service, and ultimately into our databases. And so we're going to talk today about how we leverage these data to update our groundwater models. So yeah, there's the membrane that keeps it waterproof, gets gases to the NDIR sensor, which I'll talk about shortly. And because you're measuring gases in the vapor that's adjacent to the water, using some very fundamental chemistry, if you know the concentration immediately adjacent to the water in the vapor, you can easily calculate what the concentrations are in the water. And these things most of them are battery powered. We've got them at a lot of active sites, so they need to go down in a flush mount so people can drive over them. So in that case, the batteries fit in there. In cases where it's maybe not such an active site, you can have stick-ups to have them be solar powered. They can also be directly tied into a power source on site. Usually they measure every 30 minutes to half hour. And yeah, it's automated data collection. So this is the not so secret sauce, the NDIR sensor. So really, this is the same technology that would be in your carbon monoxide or dioxide detector at home. So in this case, we've got this sampling tube, we've got an emitter and a detector, And what this does is gas is able to come in. Really, these are both inlets and outlets. We've got a highly reflective tube that, uh, in our cases, they're gold plated to allow lots of light to make it through. And this is a 2-channel example where we've got an infrared active light source. Let's say it's tuned to carbon dioxide to keep the detector, the home detector analogy going. It's going to emit a wavelength of light that it's 100% here, and it's diminished by the time it gets to the detector. And that reduction in the intensity is due to carbon dioxide. And so to get the robust estimates, you also have an IR source that's close to the same wavelength, but is transparent to carbon dioxide. So it makes it all the way through. And so you compare how much of your active filter made it through relative to your reference filter. And that difference, essentially, it's overly reductive. That gives you your gas concentrations. And if I were listening to this talk, the first question in my mind would be, okay, but does it really, that sounds great and all, but does it really actually measure groundwater hydrocarbon concentrations? Yes, it does, is the short answer. So last year we did this study. We're across 18 sites mainly in Saskatchewan, one in Manitoba, collected 100 groundwater samples. And of those, there was 45 that were above detection limits. And so we would get those set up in the lab, have our sensors measuring, and then we would take a sample and send it to another lab here in town where they would measure it on the GCFID, and then we compared the results, and it's pretty strong, mainly for the F1 BTEX fraction. You see F1 there, really high R squared, but still 0.9 for BTEX. So very close, very, very good estimates of actual groundwater concentrations. So how the data flow typically works, go to a site. The default is 5 or 6 sensors go in. Each of these sensors has a little communication module that sends the data to a gateway. In this case, it's LoRaWAN. It's just long range, low power. So it's a way that you can send data over large distances using a low amount of power. And these go to our servers where, so the data are encrypted for a number of different reasons. Part is to meet regulations, and part is for privacy. If somebody intercepts this, you don't want your data to get stolen. They come to our server where we have a decoder, and we convert. It just looks like gibberish until you decode it, and then it actually looks like real data. And then this goes to our database. And so now that we've got the data from the environment, they're into the cloud. Now we're able to leverage these in our groundwater models. So I mentioned before, we use ModFlow, and this is a component of our PlumeFutures, our plume prediction algorithm. And we incorporate our sensor data through something called data assimilation. It's basically you have an existing model here, say in yellow, and that's the state of the knowledge. Based on the data we have, here's what we think is going on. You have some new data come in, and you can update your state of knowledge here. So this is your updated model. And ideally, it would be like this, where you can see there's less spread. So you've got less uncertainty in your estimates. So you can, with more confidence, say, this is what's happening at our site. So we can convert that model into, say, a visualization over time. So what this is an animation of the plume at a site. You can see the groundwater contours of various concentrations. Maybe you can see these little blue arrows that were built off water sampling at the site that gives you your groundwater flow. And just off the site here, there is a stream. And you can see that under this scenario, the plume it's growing for a while. It's starting to fall the groundwater, but as natural attenuation takes place, it starts to shrink. And over a 30, 40-year horizon, it's looking like a rosy picture. And then finally, to be able to provide this information, it goes to our dashboards, which we're still working on. And they can just try to provide the most salient information. What do I need to know about this site, that I can look at within 30 seconds and get those information is what we're aiming for. So how is it valuable to have these groundwater models be incorporating new data all the time? Well, we'll go through two examples. So in this case, we've built a model in the yellow there, and then say there was either a new sensor went in just outside the area, or consultants went and collected more data. And you realize, oh, that's actually outside of where we think our plume is. So let's incorporate these new data into our model. And now it looks something like this. So whereas you can see on the south end here, oh, we're very confident, based on the data, there's not a lot of spatial variability in the plume extents here. Whereas where we got those new data, okay, well, if it's this concentration here, we know it doesn't just go to zero right adjacent to that. So we're a little more uncertain here. So maybe if we're going to focus our sampling efforts on just a portion of the site, this might be the prime suspect here. And then this is an iterative process. If it's whether it's field data or if it's autonomous sensors, which would give you quicker updates, you're constantly updating this model. And because I'm a little simpler, I like analogies. So this is a more general explanation of the process. That you have your initial model, you simulate new sensor data, then you get an updated model that hopefully gives you more confidence because you've got reduced uncertainty. And we talk about groundwater, so this could be plume stability, but if natural depletion is the question, or is a remediation treatment effective, that's how we can gear the model outputs. And this is iterative, so it keeps getting updated. Hopefully you're getting this reduced uncertainty. And the reason why we have this picture up here is it just reminded me of, how I went bowling last week. This is me. They have these bumpers up for people like me that, what if something goes wrong at the start, or there's something might not be up to snuff? So for instance, with data collection, maybe one of the samples isn't robust, or, it was a super rainy day, it was rushed. So you just have this one data collection and your model is based off of that. You just let it go. If you have poor data going in at the start, you might not get that strike at the end. It might not be representative of what site conditions actually are. But if you're constantly nudging that model, kind of like how these bumpers are constantly nudging the ball down, then you're reducing your uncertainty and you're putting a lot more data in. So you get a lot more confidence that, okay, what's coming out the other end is something that is probably more representative of what's going on at the site. So here, we had our engineers put together this just a hypothetical direct comparison between, say, traditional annual or biannual sampling and having autonomous sensors here and on the right. So let's say you got 6 wells. They're getting sampled once or twice a year, depending on the requirements. The sensors are sampling every 30 minutes. For the field work, you got to collect the sample, you send it to the lab, you wait for the report, and then those data have to get analyzed. Whereas for autonomous sensors, there's really no field work after they're installed, except for maybe a battery replacement a year or two down the road. And they can be removed for field sampling as well. In the analysis, you get a single point in time from a small amount of material, whereas with autonomous sensors, they're continuously updated, and that can be tied into dashboard updates. You get 1 to 2 points per well, depending if it's once or twice a year. If you're sampling every half hour at one location, this gives you almost 18,000 points over the course of the year. So if you're thinking, and this to me sounds kind of like a trend line, okay, we need to get at least 3 data points to fit a line. So that might translate to at least 3 years to gain, understanding what the trajectory is for a site. Whereas with autonomous measurement, over a period of this equilibration period for usually around 6 weeks after a sensor goes down a well. So then you collect a few months of data after that, and that starts to give you an idea of how the site is performing. The cost, we can just skip to the last one where it works out to might be between $5,000 and $10,000 per data point, whereas much cheaper when it's autonomous data. And then this highlights an example of what you can do with these data. So this is scenario planning. So there's 3 scenarios for the site. It's a baseline. This is where we're not measuring natural source zone depletion. So we're just assuming it's 0. We know it's non-zero, but we haven't measured it, so we're assuming it's 0. So this is really like a worst case scenario. In the middle here, this is quantifying NSAD, whether it's through flux traps or autonomous sensors. And then this last one, it's if you've biostimmed. And our data suggests that it's usually about a doubling of NSAD rates. So these data could come from either our site network or from actual data on the site. And so under this scenario, you can see that over about 30 years, you've depleted quite a bit of product in the biostim scenario compared to the baseline. And converting these into the mass remaining in groundwater, we've gotten like an 80% reduction using biostim compared to baseline. So at this particular site, it's not going to be the same everywhere. It looks like, okay, biostim is probably a good candidate for this site. It seems to be working well. If you don't like maps, you can put it into a graphical perspective where you look at the area over time. So this is for a different site. We've got our baseline, so no NSAD in brown, and our biostim scenario green here with NSAD in between. And you can see the improvement of biostim over the baseline and also over just natural source zone, and particularly with the mass. So the area is going up. Potentially it could be younger spills, it's still spreading, but there's no new product added. So even though it's like the same mass is getting spread out over a larger area, which gives it better depletion. So another application here is site triage. So it could be, okay, we've got these 3 scenarios. When we look at what this is, this is our baseline, NSAD and biostim. And this is time to fence line. So this could be some critical receptor on site. So in this case, we'll say it's the property line. Right? How long does it take for it to reach the property line? And it doesn't look like biostim is all that effective here. It maybe buys you another 3 years before it reaches the fence line. And time to stability, what that is once your concentration changes and area changes are less than 1% per year, then we're considering that stable. And there's maybe a little savings and stability, but not a whole lot. So biostim might not be a good option for the site, but the information we're gleaning here is that we've got probably about almost 30 years before it reaches a critical receptor. So it's still our problem. It hasn't become anybody else's problem. Whereas say we've got 2 sites in our portfolio and we want to figure out which one are we going to dedicate resources to. You can look at another site, and this one, say, it's similar. Biostim might not be the most effective, but this critical receptor, this could be a zoning change in the land use. And you can see that it reaches that critical receptor relatively quickly, say on the order of roughly 10 years. So if you had to choose between these 2 sites, say, okay, well, based on these quick images, if I have to make a decision now, we need to focus on site B for this year. That other one, we've got time. We can let it lay if we only had enough resources to go to one site. And this is leveraging our network that we've got out now of sensors that you can compare how one site is doing relative to the network. So here we've got this simple, it's just a regression line fit to the depletion rates versus the plume geometry. We've also incorporated volume into that. And basically, if you're above the line, you're exceeding expectations. If you're below, that might require another look. So this is a quick way to say, okay, I've got 20 sites in my portfolio. Most are meeting expectations. We've got 3 superstars, and there's these 2. Okay, these 2 maybe need a closer look. So we're getting into the home stretch here. So what we have here is actual data from a site that incorporates the data assimilation, but we're trying to autonomize it a little more. So we're going to say that it's a contaminated site in Mordor. And this is 200 model runs that, as new data are incorporated, by either each sampling or each new data point from the sensor, it updates its plume prediction. And so you can see as it's going, it's sort of, hopefully you can see that it's creeping out here. You get a big influx of data that dramatically changes the model. But overall, a lot of the lines are closer together here near the Sea of Nirnen. And it looks like, okay, we're pretty confident this sea is safe. We're pretty confident that this is delineation here. Whereas the data that are coming in, we don't have a lot of confidence here. So the plateau of Gorgoroth could be looking at some contamination down the line. So this could help inform future sampling efforts that got a lot of confidence here. Right? I think we got a hold on this, whereas I think we need to either add more sensors here or we need to put some wells in here to be able to be more confident about what's happening in the Northwest. So we're wrapping it up now. The recap, what EMS does for your site is getting that a lot of data to have more robust risk assessment. And because it's continuously updating, I can make decisions quicker. So it really helps with adaptive management, ideally, and helping you get further down the pathway to closure, whatever that ends up being for your site. As we saw with that table, you get more bang for your buck, get more data for a lower cost. And because the data is coming in continuously, allows you to update your predictions, because sometimes the knowledge you have at the time might, or the data that inform that knowledge, it might change. You know, you put in new wells, you got sensors in, you realize, oh, actually, our understanding of this site has changed quite a bit. So we need to update our decision for moving forward there. So this is the final slide. So I'd like to say I really appreciate all of you taking time out of your day to come and listen to us nerd out and talk about groundwater modeling. And so today we'd like to offer a free trial. If you're interested in seeing, like, you've got a site, like, I wonder, if this would be a good candidate for this, you can reach out to our BD manager, Carolyn, for more information. And what you would get out of this is you get a plume visualization, a time to stability, and if it's relevant, not all sites might have a fence line that's relevant. You can also get a time defense line. So yeah, if you're interested, please reach out to Carolyn. There's her email address. We can put it in the chat as well. And on that, we'll open it up for questions and conversation.